And since I didn't know what would be the background of the audience or the interests, I thought that instead of giving a technical talk about my work, I would give a pedagogical introduction, so to say, to some of the ideas and methods that surround my work and the work of my collaborators. So this, what I'm going to discuss is a set of ideas and techniques in collaboration with Kalin and Vicente Cortés in Hamburg, mainly, and other sometimes in collaboration with other people like Severin Bunk and hopefully others in the future. So, well, I'm going to try. This is the first time I give a talk using a live Blackboard. I hope this goes smoothly. The main idea of this or of this talk and of my work and the work of my collaborators regarding this research line is the study of supergravity as a geometric PD, right? So, in order to understand what I mean by this, we have to keep in mind an example of a PDE. Oh, sorry, what was that? An example of a PDE that has been fundamental in mathematics and in differential geometry, and which is the origin of Donaldson theory, right? So we fix a four-dimensional manifold. This is a manifold of dimension 4 with a metric G. This is a Riemannian metric. So this is a Riemannian metric, right? And on top of MG, we define a principal SU2 bundle. The structure group is not so relevant for my discussion, but just to fix concepts, this is an SU2 bundle, principal bundle, right? So this is a principal bundle defined over a four-dimensional, sorry again for that, a four-dimensional Riemannian manifold. And given this structure, so given M, G, and P, we look for solutions to the following differential system. We take the Hodge dual on the two-form part of the curvature of a connection on P, and we impose that this is anti-self-dual. As you know very well, these are the anti-self-duality conditions for a connection A on P, right? So this innocently looking system, right, is at the root of the Donaldson invariance. So from the careful study of the moduli space of solutions to this system here, this system, modulo automorphisms of the principal bundle that cover the identity, one constructs a moduli space of anti-self-dual connections modulo gauge transformations or automorphisms of the principal bundle covering the identity. And this leads to a flurry of mathematical activity, this object here, right? And this was the beginning of a subject which some people call, this gives rise to the subject, mathematical subject that some people call mathematical gauge theory, right? Which has the following motto, so to say, or the following philosophy, right? Which is as follows, consists of the following, so to say. Study or pick, choose interesting PDE systems, gauge PDE systems, namely globally defined in terms of global differential operators and having a space of solutions that has a gauge symmetry. So choose interesting PDE systems and construct the moduli of solutions modulo isomorphisms. The appropriate notion of isomorphism depends on the case under consideration. And with this, try to obtain info on the underlying manifold. So these PDE systems usually live on a manifold, and though with some extra structure, the extra structure in this case that we are going to have as a guiding principle here, is the principal bundle, but we're not interested so much on the principal bundle, but on the underlying four-dimensional manifold, right? So with this type of work in the 80s, they were able to obtain new information on the smooth type of four-dimensional manifolds. So once we clarify this principle, this ideology, if you will, then we have a natural question, which is what is an interesting PDE system, right?
These equations you consider are on what?
Sorry?
PDEs, I mean. These PDEs are defined on which manifold?
So you mean the ones that I'm going to discuss, or the ones that or the self-duality condition?
No, this interest in PDEs.
Yes.
Where they
So they are going to live on a fixed manifold, as in the case of the self-duality condition. We're going to fix a compact manifold, and though with a Riemannian metric, and we want to define an interesting, quote unquote, interesting, of course, PDE system, which is going to involve several variables that live on geometric structures on our manifold. For example, a principal bundle. We will see an explicit example of this. So hopefully this will be clarified. But the guiding principle again is this seemingly naive system, which is we fix a Riemannian manifold M, G, and though with a principal SU2 bundle, and then we consider the PDE system. This is a first order PDE system, which is nonlinear, importantly, if for the SU2 bundle, for the SU2 group structure. So this is a first order PDE for connections on P. That's our system in this case. And G, the metric is fixed. We take a compact manifold, and the variables are the connections, right? Okay, so after these self-duality equations appear, and they were used to construct Donaldson invariants by studying the topological structure of the moduli space, other systems of PDEs arise in the literature, most notably the Seiberg-Witten equations, which led to the Seiberg-Witten invariants, and the pseudolomorphicity equations of Gromov. I will not get into this. So regarding this question that I posed here, I just want to mention that this, and this is in a sense the beginning of my talk, these systems of equations together, as well as the system of self-duality equations, and this is the observation, these are all supersymmetric systems in Sugra, perhaps after, or in supersymmetry, let me say super. Perhaps after topological twists or other tricks, but these arise all or can be understood all in the context of supersymmetric field theories. So therefore, if the known interesting systems that have applicability in geometric analysis and differential topology are all particular cases of supersymmetric systems in supergravity or supersymmetric field theories, it is natural to consider interesting those general supersymmetric systems. So this provides motivation to study and classify, given that these particular cases are so interesting and important, to study and classify all supersymmetric systems. So this, what I mean is geometrically and mathematically, of course. So study and classify, then hopefully we will discover another PDE system that has applicability and applications in differential geometry and classify all SUSY systems. I will define what a SUSY system is, of course. This goes under different names. Okay, so in order to do this, motivated by the discussion that we just had, we need to then understand supergravity, because these supersymmetric systems arise and as supersymmetric conditions in supergravity theories, right? Therefore, well, this is what we have been doing for some time, and this is what I will discuss now, giving an example and, if time permitting, a couple of examples, right? Okay, so let me just clarify that, first of all, there is no general theory, no mathematical theory of supergravity. So this is not available. There is no general accepted established mathematical theory of supergravity that we can use to extract the geometric information of its supersymmetric conditions. Although these theories, of course, have been extensively studied in the physics literature, there are tens of thousands of papers about them. They are usually studied from a local point of view, in which supergravity is understood as follows. Is understood as locally as a Lagrangian system. So in terms of a Lagrangian, let me just write schematically L, calligraphic L of G, because there is always a metric, either Riemannian or Lorentzian, and a set of variables that I denote generically by phi. Okay, so this is our Lagrangian, and this is defined. These variables may depend on extra data. Okay, so it is a Lagrangian system which involves the metric as a variable and involves then a set of generic variables that I'm discussing here, denoted here by phi. For example, just to give you an idea, in the simplest n equals 1, namely minimal supersymmetry, this refers that there is only one supersymmetry generator, four-dimensional Lorentzian supergravity, so in Lorentzian signature, which is where these were developed originally. The variables of the Lagrangian, namely the matter content, as the physicists say, is simply a pair G, psi. Sorry, I don't know why this. I need to get used to this. Okay, so a pair G, psi, where evidently G is a Lorentzian metric on a manifold M that we consider fixed, and
But your manifold and metric are even, yeah?
come again, sorry?
Your manifold M and G are standard even, not super.
Not super. That's a good point. Yes. I will go back to that point in a moment. Yes. So actually, let me reflect on something here. So the proper mathematical theory of supergravity a priori involves supergeometry, needs to be developed using the framework of supergeometry. That's what seems more natural. However, doing so, well, requires a different set of tools, techniques, and a different community from the one I'm discussing here, and takes us away from the goal I want to discuss. However, everything is compatible because in a sense, what I'm going to discuss is a system of PDEs that you extract from supergravity by truncating the fermionic sector. Okay? And I will explain why, even after doing that, you have a remnant of supersymmetry, which is actually the system of supersymmetric conditions that plays an interesting role in geometric analysis. So I will not discuss supergeometry. That's a fundamental topic that I would like to understand better. But still, you can say a lot of things about supergravity without using supergeometry. And in fact, for example, this simple 4D theory that I'm going to mention here, you can fully describe it without using supergeometry. There is a proper geometric description of this theory, complete, with the fermionic sector as well, without using supergeometry. And you can check this, for example, in the book by Thomas Ortin, Gravity and Strings. He constructs it explicitly, and he proves without using supergeometry that the theory is supersymmetric. This is gravity and strings. Okay. Here, I just wanted to give an example of what these variables could be. So here the variables are a Lorentzian metric on M and a one form taking values, one form on M taking values on S, where S is a bundle of irreducible. Let me move this. Irreducible real Clifford modules. Okay. And this is what is usually called or referred to in the literature as the gravity. So in this case, we only have a metric and its quote-unquote supersymmetric partner, which is the gravitino, which takes values. It's a one form on M that takes values on a choice of bundle of irreducible real Clifford modules, so a choice of irreducible real spinors on M. Okay, so in this case, well, you can see the matter content, the variables of the system are relatively simple to explain at least, but other supergravity theories can have a spectrum of variables which is much more complicated, right? So,
sorry, Carlos, so the metric is a background or it's a dynamical field?
That's, and again, a good point. It's a dynamical field. So what characterizes supergravity here is that the metric is always dynamical. Otherwise, we would be talking about a supersymmetric field theory, right? So that's an interesting ingredient of supergravity, which makes much more difficult the study of its moduli space of solutions, because one needs to consider as part of the automorphisms of the theory the diffeomorphism group of the underlying manifold. So this is always something that one has to face when studying supergravity. So a way that I like to discuss or explain what follows.
But this bundle, so I don't know what you call Clifford
Spinor bundle, basically.
But this is a bundle over what?
This is a bundle defined over the space-time, if you want, over the four-dimensional manifold on which the metric lives. Yeah, this is a spinor bundle. The only thing is a very specific spinor bundle, right? There are many spinor bundles you can define on M, G, and this is one precisely such that it's a bundle of irreducible real Clifford mode. Usually, supergravity is very picky with the spin or bundles it requires to be formulated. So it's not a random choice. There are some conditions. So what I want, one way that I like to explain or in a way in which I like to explain what follows for mathematicians is the following. So yeah. So if for the physicists in the audience, they might think this is too naive, but it's a way that I find efficient to explain the following to mathematicians, which is that this system of variables so the variables of my system can be split in two categories or in two sets, right? One which I call bosonic and one which I call fermionic.
I'm sorry, Carlos. So
yes.
just a question. So because I asked about the variability of G. So this is a dynamical field. So you will consider variations of this field, but you will consider variations of the metric within the class of spin manifolds, right? So M with G has to be a spin manifold always, right? It will be like a constraint. No?
Not necessarily. So for this,
you have a spin bundle over Mg, so no?
Well, yeah. So for spin bundles can exist without the underlying manifold being a spin, right? So for an example of this appears in, for example, Seiberg-Witten theory, and it's crucial because not every compact four manifold admits a spin structure, right? But the notion of a spin C structure that occurs in Seiberg-Witten theory and that allows to construct a spin or bundles associated to it is much more general. So for this simple case, in which we only have n equals 1 supergravity without matter content, yes, here we need the manifold to be a spin. But other more complicated supergravities, and hopefully I will describe one in what follows, can be defined using more general notions of a spinorial structure, such as a spin C structure, right? Or a spin Q structure even. And well, just let me just clarify this. So this is a small digression right here. So we may need, rather than a spin structure, a spin C structure, which is essentially a spin dot U1, or a spin Q structure, or H, sometimes it's called H, which is a spin dot SP1. So these are more general notions of a spin structure, which occur in different dimensions and signature, and which still allow or imply the existence of a spin or bundle. But either way, indeed, we have to impose some condition on M, which ensures the existence of a spin or bundles, yes. But then once you impose that, essentially, then it doesn't depend on the metric chosen. So especially in Riemannian signature, it doesn't depend on the metric chosen. Because all reductions of Riemannian metrics are equivalent. So within this context, we have a local Lagrangian, I recall, with variables phi. We can divide these variables into two sets. One, which I call fermionic, which are those variables that take values on a spin or bundle. And then I call the bosonic those that don't. So these take values on a non-trivial spin or bundle. I call them fermionic. I know physicists have a very different way of defining fermionic and bosonic degrees of freedom, but mathematically speaking, this description is very clean to be explained. And then the point of this Lagrangian local Lagrangian that defines supergravity with this system of variables, one that do not take values on spinor bundle, we can think of this as a standard tensors or similar objects, familiar, and other variables that takes values on a spinor bundle, which we call fermionic, is that this Lagrangian gives rise to some equations of motion with the standard procedure, variational procedure, motion, that are invariant under SUSY. So what is this? So this means that my choice of Lagrangian and variables comes equipped with a choice of a spinor bundle. And for every section of this spinor bundle, I have a what I call an infinitesimal transformation generated by this spinor bundle, which this is very schematic, sorry, assigns or maps bosons into an expression involving the supersymmetry generation and fermions, and all the way around. This we can call.
Excuse me, but more formally, this is an action of a certain super Lie group on the space of fields, yes?
Yes. So let me say something about that.
In the big picture, we have fields that take value in some fiber bundle that carries a structure of a supermanifold, and we have an action of a super Lie group on this bundle, yes or no?
Yeah, let me say something about that. So, since, as you will see in a moment, I will be truncating these infinitesimal transformations. I know there are several proposals to the mathematical structure underlying these transformations on superspace. I don't know if any of these proposals is an established theory for what a supersymmetry transformation is beyond the infinitesimal level. So I don't know about the mathematical structure of these transformations as transformations in superspace, right? Because as I will describe in a moment, what I'm interested in is a remnant of these infinitesimal transformations that can be globally well-defined when we truncate the fermion fields. So let me clarify what I mean. Once we have this notion, even without worrying too much about the mathematical structure of these transformations, these are local expressions on the fields of the theory and the given supersymmetry parameter, and they give rise to the notion of supersymmetric solution of supergravity theory, which is a configuration that satisfies the equations of motion, so satisfies the equations of motion of the theory derived from the Lagrangian, and is preserved by supersymmetry. So is preserved by this infinitesimal transformation. And now, what's the final point? The final point is that if we understand supergravity as a fundamental theory of gravity, a very natural condition to obtain or study physical solutions is to impose that the fermions are zero, because macroscopic gravitational systems do not have visible fermionic degrees of freedom. So we take all the fermions of our Lagrangian theory to be zero in the sense of being sections, of being the zero section of the spinor bundle. Okay, and the point is that this is always a consistent truncation, right? And this consistent truncation gives rise now to a Lagrangian, which is much simpler for the metric and the remaining bosonic degrees of freedom, which gives rise to equations of the following type. Ricci of the metric equals some symmetric tensor depending on the metric and the bosonic fields. So this is the Einstein-like equation. This is an Einstein-like equation. And then some equations, let me just call them of the bosonic degrees of freedom, right? So supergravity, yes.
If I may, because I'm now a little bit confused, because at first you told us, am I right, that fields of the theory were taking values in this in some tensor power of this spinor bundle, but now you take symmetry transformation parameters as sections of this bundle, so I'm confused.
Yes.
Typically, so it's like the types don't agree, at least it would seem. Yeah, could you comment on that? Because, yeah.
Yes, so
it is unusual to say that you vary one field relative to a small field of the other type, a dynamical one. I'm confused now.
So I don't know if I understand the question, sorry, but let me clarify and then please tell me if this helps. So usually every supergravity theory, let's go back to this simple example, requires choosing a spinor bundle. So that's fixed. For every metric G, we have a choice of a spinor bundle. This can be done coherently for all metrics. And now, once I have a configuration which requires fixing a metric, then I have a spinor bundle. And then that's the new ingredient of supersymmetry in a sense, which is that symmetries are not necessarily generated by tensors, but in this case, the generator of supersymmetry is a spinor field. So with this spinor field, I construct a local expression which involves the fields of the theory and which I call an infinitesimal supersymmetry transformation. And yeah, I don't know. So what worries you?
Am I to think of it in the following way, that the spinor bundle, you superize it, you take like it's, you think of it as a source of those colloquially so-called Grassmann variables. Is that the thing?
Yes.
We're not to think of the dynamical fields in your theory as being sections in this spinor bundle, because then it would make no sense to say that we vary along sections of this spinor bundle. The spinor bundle plays an auxiliary role as a source of those space-time dependent Grassmann variables, as physicists call them. Yeah, which means that you have to superize the fiber.
But it makes sense to why do you think it doesn't make sense to take the?
No, I'm just asking. It's unusual for me to have a field which takes values in some bundle. But then I think of the bundle of a space-time as a configuration bundle of my field theory, and then I say that a symmetry transformation is given by a global section of the same bundle. Global sections of that bundle then are typically understood as types, as fields of the theory, dynamical field.
Well, no, but let me give you an instance. For example, I know. Now I understand. Yeah. So indeed, sections of this spinor bundle, can be considered as fields because some matter content takes values in this spinor bundle. But the sections of this spinor bundle can also be considered as generators of symmetry, supersymmetry in this case, that are not fields. And a similar example happens if you want in standard gravity. So generator of a diffeomorphism is a vector field, right? But the matter content of your theory can have also vector fields as part of the variables of your theory. It's not incompatible. In one case, a vector field is a generator of symmetry because it generates a family of diffeomorphisms which act on the metric via the Lie derivative. The Lie derivative of a metric along a vector field is the analog, is the standard bosonic analog of these supersymmetry transformations. Delta epsilon will be LV, meaning that this is just an analogy to explain my point. This Lie derivative of the metric will be a infinitesimal transformation generated by a vector field. This is supposed to be vector fields, right? Of the same type, this is morally the same as this transformation, but these transformations are generated by a spinor. And in this case, your theory, for example, if you couple it to a local Maxwell field, that's locally a one form that you can dualize on a vector. So you would have local vectors as variables and vectors as generators of symmetries. I know it's...
Yeah, this could be the same situation like in mechanics, where the second tangent bundle you have. So you get two types of vector fields. One is the dynamical, and the other is related to variations. Yeah, so one vector field, one understanding of this vector fields is as describing variations, and the other are dynamic.
Yeah. So here, this supersymmetry generator indeed is not dynamical. And the point is that after we truncate our theory, we get this simplified Lagrangian. We take to be zero all the fermionic variables. We end up with an Einstein-like equation. So rich equals something. This is Einstein-like. This is, if you want, the reverse energy momentum tensor of the theory, and some equations for the bosonic degrees of freedom. So if this was all, then the bosonic truncation of supergravity wouldn't be so interesting, because this is a hard second order PDE system. This is a second order PDE system. Right? Which is a particular case of a general relativity system. It's metric coupled to some matter governed by the Einstein equations, everyday Einstein equations, and satisfying some extra conditions for the bosonic sectors. But the key point is that in this construction is that there is a remnant of supersymmetry here. Even if we have truncated all fermionic degrees of freedom, there is a remnant of SUSY, right? Which appears as follows. It still makes sense to talk about supersymmetric bosonic solution. So this is a solution that is preserved by supersymmetry. Even if it is bosonic, it is preserved by supersymmetry. So if we go back to this schematic setup here, right? We want these transformations to vanish in order to have a supersymmetric solution, and this goes right to my point. So, well, I will not write this again because it's already written here. Let me just save some space. So we want this to vanish on our solution in order to be supersymmetric, but we are taking this to be zero. I'm taking this because we are at a bosonic solution. So taking this to be zero makes this thing vanish completely. So this poses no further condition. But this, making this to be zero, is non-trivial even on a bosonic background. So therefore, and this is the key point of the mathematical interest of supergravity in this context, there is a notion of supersymmetry that for a solution of the equations, solution of equations of motion, second order, difficult. We have a notion of supersymmetry, which is that this guy, which are the fermionic variations, this guy is zero. This defines a subclass of solutions, which are the supersymmetric bosonic solutions. And mathematically speaking, this is what I will discuss now. This becomes a spinorial first order PDE system. And this is where all the mathematical interest lies, first order, or most of it. Remember that when we mention these anti-self-duality conditions as a canonical example to have in mind, the anti-self-duality condition is a first-order PDE system, right? And the main point of supersymmetry in this context, which was so profitable in the past, and in the future it will be as well, is that if you have a bosonic configuration that is not necessarily a solution, bosonic here. So this is a configuration that is not necessarily a solution, but there exists a spinor such that this is zero. Then you, for free, by solving this system of first order equations, almost satisfies all, you can satisfy all second order equations of the original system. So the equations of motion follow from this first order system, which so you are discovering a type of first order integrability in very complicated general relativity system. Equations of motion, almost. Almost mean here that depending on the spinor, some components may not be satisfied, but for example, in Riemannian signature, this is a strict implication. So what is this mathematically? What is this type of condition? This type of condition is as follows. And these are the supersymmetry conditions of supergravity. These are given by a connection on your spinor bundle, which is constructed out of the metric and the bosonic degrees of freedom equals to 0. And I will explain now. And the endomorphism of the spinor bundle, again, depending on the metric and bosonic degrees of freedom, acting on your spinor equals to 0. This is a supersymmetric system. This means that with the bosonic content of my theory defines a connection on the spinor bundle, which is not Levi-Civita in general. And then a solution is a spinor field that is parallel under this equation, under this connection. And on top of that, it belongs to the kernel of a given endomorphism that is defined with the fields of the theory, right? So this is what physicists sometimes call the Killing spinor equations of supergravity, or the supersymmetric conditions. And all these interesting mathematical PTEs that have been studied in differential topology are particular cases of this system. In particular, just to close the loop, the self-duality condition that we described before, right? Remember, this Hodge dual of curvature equals minus curvature. This is equivalent to the curvature of A acting via Clifford multiplication on an irreducible complex chiral spinor equals 0. And this is an equation of this type. The endomorphism here is the curvature acting via Clifford multiplication. So this is how you recover, or you explain, the self-duality condition as a supersymmetry condition. It can be equivalently written in terms of a condition for a spin, right? So, well, the simplest case is the n equals 1 supergravity we were mentioning before, right? Remember that n equals 1 sugra minimal, we only had as variables the metric and the gravitino, right? Which was a one form taking values on the spinel bundle. But we are saying that we truncate all fermionic degrees of freedom, right? So we take this guy, which takes values on the spinel bundle to be 0. Then n equals 1 supergravity reduces simply to a theory of metrics, Lorentzian metrics on M, which are Ricci flat. This is what comes out of the theory when you truncate the gravity, right? And what's the supersymmetry condition in this case? Well, since there is no matter, there are no bosonic fields other than the metric, what you get here is that a Ricci flat metric is supersymmetric if and only if there exists a spinor which is parallel under Levi beta. In this case, this connection reduces to Levi beta. So this fits within the framework we have explained here. This is 0. There is no endomorphism because there is no bosonic degrees of freedom. And this complicated connection in terms of the bosonic fields, since there are no other bosonic fields, reduces to Levi beta. So Ricci flat metrics that admit a parallel spinor, in the sense we mentioned before, earlier, are the supersymmetric solutions of n equals 1 supergravity, minimal. But this condition is quite non-trivial and quite interesting mathematically speaking. Physically, this gives rise to what physicists call PP waves, essentially. So these are examples or particular case of idealized gravitational waves. And have very interesting geometric and topological structures. But this is just the simplest case. So in order to give you a more interesting, perhaps, and a relevant case for string theory in particular, I will consider now, I wanted to consider another example, but I am afraid I won't have time. Neves-Schwarz supergravity in 10D. So remember, within this geometric setup, we describe the bosonic sector. When I mean supergravity, I describe the bosonic sector plus its SUSY conditions or Killing-Spinor equations. I'm not describing the full theory with its supersymmetric transformations. This is a truncation that can be described using global differential geometry and topology without going to supergeometry, and which gives rise to the moduli spaces of solutions I'm interested in, right? So this Neves-Schwarz supergravity, because of the occurrence of the B field, requires a more sophisticated geometric structure to be defined, right? So instead of a bare manifold, to describe this theory, we need to choose a bundle jar. This is one model that you can use to describe this theory. A bundle jar, which is a categorification of the notion of principal U1 bundle. And we can think of here as a triple Y, let's say, or let me say, P. I'm just explaining here the geometric structure you need to formulate this Neves-Schwarz supergravity in 10 dimensions, right? So we need a bundle jar, which we consider as a triple PYA, where this Y is a submersion. P is a U1 bundle on the fiber product of this submersion with itself, right? And, sorry, A, sorry, this A is a connection on P, which satisfies consistency conditions. So this notion of bundle gerbs was introduced by Murray in the 90s. So this is by Murray in 96. And gives a very down-to-earth, so to say, geometric realization of H3, right? So in the same sense as U1 bundles give a geometric realization of H2 over the integers, singular cohomology, these bundle gerbs give a geometric realization of H3, which is required by this type of supergravity precisely because of the B field, right? There are other models for gerbs that you can use. This is just my preferred choice in this context, right? So let me give a definition here. So a curving on this bundle gerb is a two-form, not on M, this is important, but on the on this submersion. So this is a two-form B on this submersion, on the total space of the submersion, such that it's pullback. This is the pullback via the simplicial differential generated by this submersion is equal to the curvature of this U1 bundle connection, right? So this is the famous B field in supergravity or string theory, at least in the context of this theory, is the B field. So the B field is a curving on a choice of bundle gerb. Okay, so with these provisos in mind, we can define the configuration space of the bosonic theory, which depends on a choice of bundle gerb over M, are triples G is the Lorentzian metric. B is a curving on the gerb. And then we have the dilaton, which we can model in various different forms, but for simplicity, we can take it here to be a real function on the base space. This is the dilaton, although it admits more general and interesting models. But for simplicity, let me just say that the bosonic configuration of this space, of this supergravity theory, and incidentally of the corresponding string theory, but here we are just discussing supergravity, are triples of this form. So this couples a Lorentzian metric on M to a curving on a gerb to a smooth function that we call the dilaton. So now, what are the equations of motion that follow from the Lagrangian, right? That follow from the supergravity Lagrangian. I could write the supergravity Lagrangian, but let me just write the equations of motion, which is the geometric system one needs to solve, right? And as promised, it's going to be of the type that I described before. So these are, we have first the Einstein equation. This is the Einstein equation, which is that the Ricci curvature of the metric plus the covariant derivative of the curvature of the dilaton. Here in this particular setup, this curvature is simply d of phi, but in other more interesting geometric models is something more complicated, minus a contraction of the curvature of the curving equals 0. So this is the Einstein equation of this supergravity theory. Here, HB is a three-form that plays the role of the curvature of the curving B. This can be defined using the simplicial differential, and is the analog of the curvature of a U1 connection on a bundle, U1 bundle. The difference is that, of course, the curvature of a U1 bundle is a two-form, while the curvature of a curving is a three-form, which is precisely what supersymmetry requires. So this is very fitting, right? And this contraction here is simply a way of writing this type of contraction. So this is a symmetric tensor, Ij, and we can think of this as H modulo factors, HILM, HKLM. Okay, so this is the first equation of the system. It's an Einstein-like equation, relatively complicated. Then we have what people call the Maxwell equation, which is this is the equation for the metric, right? This is the equation for the curving, which is called sometimes the Maxwell field of the theory, because plays the analog role of as the Maxwell field plays in Einstein-Maxwell theory. And this is that the adjoint of the Levi-Civita connection applied to the curving, the curvature of the curving, is equal the curvature evaluated on the gradient of the dilaton. Okay. And then the third equation is the dilaton equation. And this states that, again, this adjoint plus this is a square, this square equals the norm of the curve, of the curvature of the curve. So this is the bosonic system that corresponds to 10-dimensional supergravity, to the common, what people say the common sector. So the simple model, the simplest model of 10-dimensional supergravity. We have a gravitational theory, we have an Einstein equation that couples to a B field and a function that we call the dilaton and satisfy this complicated system of equations. In this generality, it's even hard to construct a solution that is non-trivial in all fields, but you can check, this is, I will just mention in passing by, that manifolds of type S1 times S3, as defined by Goduchon, are particular cases, are examples of solutions, just to clarify this, of four-dimensional solutions. These are manifolds that are covered by S1 times S3 with an adapted metric and dilaton structure. I mentioned that just to state that there are solutions. But now the interesting point is not this complicated second-order system, but the interesting point now is what are the supersymmetry conditions for these bosonic configurations? And the supersymmetry conditions, we remember, need to be of the form metric connection on the spinor bundle equals to 0 applied to the spinor, and this endomorphism acting on the spinor equals to 0. So this is the generic type. So let me write now what are the corresponding ones to this specific supergravity. So for every...
Excuse me, there's a technical comment. You have formally approached the end of your allocated time. So
Yes. So can I have 5 minutes just to finish, just to give this?
yeah,
this...
definitely. It was just, I mean, a warning.
Okay. Okay. Yeah. I won't take too much of your time.
5 minutes. 5 minutes is okay.
Okay. Thanks. So, okay. So given a choice of configuration, which is a choice of triple metric, curving, and dilaton, we choose a spinor bundle of over our 10-dimensional manifold Mg. And in this situation, this must be a bundle of irreducible Clifford modules again, bundle of irreducible real Clifford modules. And you can check that in this dimension and signature, the volume form squares to the identity in the Clifford algebra, right? So we have a notion of chirality, consequently, and our spinor bundle splits as S plus S minus. Chiral components of our spinor bundle, which are real vector bundles of rank 16. Okay, so my supersymmetry parameter is going to be a section of one of these bundles, depending on conventions, can be plus or minus. So let's say plus. And then the supersymmetry equations adopt, which, don't forget, these are the supersymmetry transformations restricted to a bosonic configuration, which is what allows us to give this global geometric formulation. So these are given as follows. First, we have the one corresponding to the gravitino transformation, which is that this equation is satisfied. And the second one, I will explain now what that is, which is that this equation is satisfied. So what does this mean? This means that, well, first of all, this is the unique metric connection with torsion totally skew and given by the curvature of the curving. So this gives, supersymmetry gives a natural notion of Lorentzian or Riemannian geometry with torsion, where the torsion is given by the curvature of the curving. So this is very interesting geometrically. And then this is just Clifford multiplication of the curvature of the curving needs to be Clifford multiplication of the dilaton. So the statement is that a configuration B phi is supersymmetric if and only if there exists a spinor section such that this system is satisfied, holds. I mean, this one here, this. And this is a spinorial PDE first order system. And I don't know if you are familiar with the Hall-Strominger system that's playing such important role now in the mathematics, in geometric analysis. This is the origin, the building, the main block of the Hall-Strominger system. So I ran out of time, but at this point, let me just finish by saying that this, together with the previous discussion and the general notion of supersymmetry condition for a bosonic configuration, is what led Kalin, Vicente, and I to develop a general theory of, or a geometric framework, geometric framework which we call the theory of spinorial polyforms. To study equations of this type, generic equations of this type, Now we know why we chose this type of equation, because every supersymmetric system is of this form. And what we gave in this, you can check in Cortez, Lazaroyu. This is from 2020, I think, in Mathematische Zeitschrift. So what we gave is a geometric framework to study this type of equations in terms of an associated polyform, which is the square of the spinor. And the reason why we chose this particular form of equations is because they recover all the supersymmetric conditions that arise in supergravity, and these have played a role in the past as interesting PDEs whose moduli space carries information of the underlying topological manifold. And well, this will be the beginning of the discussion of our work, properly speaking, but it's the end of this talk because I'm over time. So I end here. So thanks a lot.
Thank you.
Thank you. Are there any questions, comments, short ones?
I have a standard question. So how supergravity could manifest itself in the real world?
Yeah, that's an interesting question, which I ask myself, physicist, and I have two takes about that. The first take is that from my point of view, I don't care that much if supergravity manifests itself in the real world or not, because I'm interested in the mathematical applications of supergravity, which already exist. For example, just to give you one. Thanks to supergravity and the associated CMAP construction, which is a construction done by physicists in supergravity, they discover a new mechanism to construct quaternionic Kähler manifolds from projective spatial Kähler manifolds, which is an important result in mathematics. So in that line of thought, I'm interested in supergravity because of its mathematical applications. Now, on the other hand, also, I will be very happy if supergravity was, aside from being interesting mathematically, was also interesting physically speaking, right? And as regarding that point, I cannot say much because that's far from my field of expertise. But as far as I know, n equals 1 supergravity with an adequate choice of superpotential is a good candidate model in cosmology. I don't know. I mean, Kalin Lazaroyu knows much more than I do about this, but I think that's a promising set of theories for cosmology. I don't know how that will end up, but beyond particle physics, there is applications of supergravity in cosmology that I think are very promising.
Would you advise any, maybe not necessarily written in a very strict mathematical manner, and a review work on the topic you discussed today, so that we can look for inspirations for some supergeometric structures in physics?
Yes, so that's a good question. A good starting point, perhaps, is the book that I mentioned by Tomás Ortín, Gravity and Strings, but it's a physics book, and he will describe how you go from a supergravity theory, you take this fermionic truncation, you get a very nice bosonic system with some Killing spinor equations, and he does everything very geometrically, so that's very interesting. Then, regarding the particular case of the Hall-Strominger system, which these are the, essentially speaking, these are the supersymmetry conditions of the heterotic supergravity. There are now many works in the mathematical literature. You can check, for example, the lectures on the Hall-Strominger system by García Fernández. Who is at ICEMAT in Madrid. So this is now purely geometrical lectures. There are This is a very interesting system from the mathematics point of view in the context of non-Kähler complex geometry. So about these specific sets of supersymmetry constraints, there is mathematical literature. And then more generally, there is very little mathematical literature because this is a system that has not been absorbed yet fully in the mathematics literature. This is something that we are developing, actually.
So I have a question. So you mentioned the gerb behind the curving. I'd like to ask the question: other than imposing integrality conditions on H, does it play any role? Because I mean, it is largely overlooked as a structure that identifies the gauge fields, the ordinary gauge fields in string theory, superstring theory, or whatnot, as gerb-twisted objects. So there's a gerb in the bulk, and you have a D-brane which supports a gerb module rather than an ordinary bundle. But I don't see any gauge fields, and I just see the metric and the dilaton, and then B, which happens to come from the gerb. But does the fact that it comes from the gerb play any role here?
Well, I think that's...
You have to choose your age carefully, I agree. But other than that, it's a big word. So what?
So I think that's a wonderful question. And my answer is the following. It appears that it's not so important because, as you're saying, in the equations of motion, everything appears through H. So one could think that choosing H integral or whatever is enough. But actually, it's very important in order to study the moduli space of solutions, because the moduli space of solutions involves the curving modulo the symmetries of the bundle gerb. And that's a very, very different moduli space than if you consider instead the moduli space of three forms, let's say, quotient by differential.
So that's precise. So the question is, do you actually, because this is what happens in the two-dimensional sigma model, for example, that rather than considering, say, isometries of the target space, you insist on the existence of their lift to gerb automorphisms, and that restricts the choice of the admissible, if you will, pre-quantizable symmetries very, very seriously. And now you seem to be pointing in the same direction, that you insist on the existence of a lift of symmetries of M to the gerb over it.
Exactly.
And that's
exactly. That's fundamental for studying the moduli space in the same sense as in the case of U1 connections or principal bundle connections, the self-duality equations that we mentioned before, which I had here. If you look at these equations, they only involve the curvature of the connection. But we cannot take, this is an analog situation, but simpler because it doesn't involve gerbs. So we cannot take the curvature as the field itself. Even if the connection doesn't appear explicitly, you need the connection to be the variable, because when you study the moduli space, you want to quotient by automorphisms of the principal bundle, or, as you are saying, symmetries on your manifold that lift to the principal bundle. So I'm just saying that this already happens in this more familiar case of principal bundles, and this is indeed fundamental in this Neves-Shor supergravity. Not only that, if you want to study evolution problems, in which, because this system of equations comes equipped with a Cauchy problem, and this is an evolution problem for the variables of the theory, then in order to properly pose this evolution problem, you need to consider the B field together with its symmetries as variables of the system.
But then shouldn't supersymmetry itself lift to the gerb? This is, of course, if you start with a supersymmetric sigma model, this is what happens.
I mean, it is sort of built into the structure of the super sigma model, and it makes sense to ask the question. But my question would be, shouldn't you lift supersymmetry to the germ? Of course, for that you would really work with the supergeometric setup to begin with, which you seem to be avoiding somehow, or maybe it is in the background. But the question, can you make sense of the question? Lifting supersymmetry, or this gauged supersymmetry to the germ.
Yes.
Because that's what you would have to do, actually, right? It seems.
Well, as you're saying here, since we are considering this bosonic truncation, we only have this remnant of supersymmetry that we call these Killing-Spinor equations, which are geometric PDEs. But your question still makes complete sense. And you could think of this system being simplified if you find a right notion of lift to the so-called total space, because now that's divisible, of the bundle germ. Yeah. This is not explored in this context, but I think it makes sense and perhaps gives a more geometrically more palatable description of the system. You can also, for example, lift the self-duality condition for a connection to the total space of a principal bundle, where it becomes similar. You don't gain that much, but you can do it, and in a sense, it clarifies some aspects. So I wouldn't be surprised if this is a nice thing to do here. And to answer your question within the general context of supergravity in the supergeometric framework, there I'm not so familiar with that, so I cannot answer properly. But I would imagine as well that there is a proper notion of, let's say, supergeometrization of this setup, which makes sense there and which becomes more elegant if you are able to lift it to the total space of a germ. Yeah, but for the geometric applications we have in mind here, this is enough. But yeah.
Okay, so thanks a lot, and seems like it's time to close our session today. So thank you, Carlos.
Thank you very much.
Yeah, and we'll see what happens next week. Might be the end of the world. So thanks a lot, and
thanks a lot. Bye bye.
Bye bye.
Chodzi o to, że możesz